Oh, it's 1 o'clock, so let's go right ahead. Thanks everybody for coming. Yeah, apologies for these continuing audio issues. I think something in the Zoom client has changed, and my Chrome OS doesn't like it. Anyway, welcome back. Let's see. I'm going to pause here. I checked our spreadsheet. There weren't any questions there, but any questions at this point?
No, Gerd.
Okay, good. Then I'll just jump right in. Last week's highlights, we had a few announcements. Number one is John Reedy wrote a blog post about HSDS, that's the highly scalable data service container types. Interesting read if you're interested in HSDS and so forth. I'm not going to go through it, but I think it's a good article. Then there is a webinar coming up, an introduction to HDF5 for high performance computing, data models analysis, and performance. I guess there's a hyphen missing here somewhere. Scott Breitenfeld will present that. It's a two-part talk, that's my understanding, and registration is free, but you have to register. And then I included the link here. And then, yeah, until HDF 5.113.2 comes out, VFD Swimmer Beta 2 is still available for testing, but then, yeah, it will be released with 1.13.2, so then you don't have to use the beta branch anymore. But that, yeah, is going to be early August, I guess, when 1.13.2 comes out. On the forum, interesting enough, it was all quiet. I couldn't believe it. I checked today, and yeah, I mean, there was one new post there earlier I saw, but all the others were 7 days or older. So it makes me think that everybody must be happy, which is good. But who knows? Maybe something more has happened. Anyway, so I'm going to pause once more. I've prepared something about HDF5-style data type conversions. I think that's an interesting topic. It came up in a use case recently, and so I wrote a little example, and I can use that for double duty here. It made someone happy, but then I can also present it here. But before I do that, are there any other questions? No? Okay, then I'll jump right in. So first, maybe the use case. So this was a use case where in experimental facilities or in physical experiments, frequently experimental data that's acquired really comes in the form of, most generally speaking, bit fields. So they're just fields of bits that are sampled with some frequency, and then sure, there are call it conversion routines or conversion tables that convert them into maybe voltages or something like that, and then those voltages need to be converted into engineering units of some kind to turn into something meaningful that an analyst or an engineer can do something with. And now, if you think about that, okay, certainly in HDF5, we have a bit field data type. There are a few predefined, I think up to 64-bit predefined bit field data types, but you can certainly define bit fields of any length in HDF5, and so you get started. But then in the light of this use case, you might ask, well, does that mean that I'm going to acquire data as bit fields, but then do I really need all these secondary copies? So the first stage, let's say, from bit fields to voltages, and then from voltages to whatever, whether it's a gyroscope or something that supposedly measures velocity or something else, or pressure, and so there is no intrinsic reason to have multiple copies, as long that conversion can be done efficiently. And so, yes, there might be other reasons why you would keep multiple copies. For example, performance. If this is a relatively expensive operation to convert these bit fields into physically meaningful quantities, then you may as well opt to have a secondary copy. But then you definitely want to keep the original data. So that bit field data is certainly the archival copies. That's sort of the golden master that you would never discard. You will really want to keep that because these experiments are typically very expensive to conduct, and you really want to know what was the original, the as recorded data, if you wish. Now, so let's assume that operation going from bit fields to a physical unit is feasible in the sense it can be done computationally without a whole lot of effort. How would you pull this off in HDF5? And the answer is, the first thing that might come to mind might be, can I use some kind of filters? So filters that we usually use for compression, but you can also use them as filters. Now, unit conversion, abstractly speaking, is not exactly a filtering operation, but the more fundamental problem is, remember, so let's say we recorded these bit fields in a data set, and let's say it's a time series for argument's sake, so it's going to be maybe a one-dimensional data set of a bit field element type. The problem is, of course, when you apply a filter or a sequence of filters to that, filters do not change the data type of that data set. So when you read from a data set that has filters applied to it, if it's defined that the element type is a bit field, well, then whatever the filter does at the end of the day, it's going to be a bit field. So filters might be a good first idea, but it's not going to work. So although there is a technical twist, and I come back to that at the very end. Now, so the idea is that the fact that it's the same data type also gives us a clue, which is that, we have to do some kind of data type transformation if we want to pull this off. And it's actually interesting that this concept of a data type transformation, in the sense that you are reading from a data set of a certain element type, and then the in-memory data type is actually different from the in-file type for reading, but also the same goes for writing. Let's say you're writing from an in-memory type to an in-the-file data type. That idea was there in HDF5 from the very beginning, and in particular, the idea of very simple data type transformations. So let's say, for example, widening a type, so going from integers to floating point numbers, for example, or floating point numbers truncating, or in the case of endianness, to switch between endianness. So that concept of a data type transformation was actually in HDF5 there from the very beginning. And there is, like the filter pipeline, there is actually a sort of a data transformation, not pipeline, but stage as part of when you execute a read or write operation. And so the example that I'm going to show you where I think this will become clear how this can be done is, so what I'm going to do is I'm going to use a bit field in memory as my data type. And then let's say I would like to store this bit field as a compound type that has two fields. That would be an example of such a data type transformation where I'm going from bit field and I'm writing this to a data set in an HDF5 file whose element type is a compound. And conveniently, as you will see in a moment, I'm just going to use a bit field with 32 bits, which you can, if you wish, interpret as an unsigned 32-bit integer. And I'm going to use that to printf the data set just for everybody to see what's there. but abstractly, a bit field is not an integer because the set of operations that you do on integers is different from the set of operations that you do on bit fields from a just abstract data type perspective. But then, yeah, so I have these 32 bits, and what I'm going to do is, for my compound type, I'm basically, to make this transformation not too complicated, I'm just going to split it into two 16-bit bit fields, but then interpret them as just unsigned 16-bit integers. And so I'm going to have a compound type that has two fields, and I'm going to call it low and high. And then basically that's the compound data type as which I'm going to store it in HDF5. I didn't prepare if you said, well, couldn't the HDF5 library do it on its own? In some abstract sense, perhaps, but if you did that without thinking about it too much, so let's say you define a data set in memory as a 32-bit bit field, and then you define a second data set in the file with this compound type that has these two fields, and then you do an H5D read or H5D write, you would get an error. The HDF5 library would basically throw an error, and the error message would say something to the extent that there is no conversion function to convert from the in-memory, in this case, the in-memory data type to the in-file data type. And I should have done this now that I think about it, but I didn't. So I can assure you that if you do this with the vanilla HDF5 library, this is the error message that you're going to get. So the library will basically say, sorry, I can't do that. Again, it would work, for example, if you were to write from an integer data set to a floating point type data set, that would be fine. Or from a floating point like a 32-bit to 64-bit, and as long as there is no overflow, you could even write from a 64-bit to a 32-bit data type. Those are things, type of data type conversions that the compiler can generate for you, so there are no issues there. But for this example, or yeah, let's say you want to write strings to a floating point number data set, and so all these not by default convertible transactions, I shouldn't call them transactions, operations, read-write operations, would create an error. Now, again, in the HDF5 files and in the HDF5 library, since this is a concept that has been around for a very long time, you have the ability to, in addition to we call them hard conversions, the compiler-generated data type conversions, you can define so-called, we call them soft conversions. So if you provide a function that does the conversion from a source element type to a destination element type, you can register that conversion function with the HDF5 library. And then once you have that registered, whenever you do a write, for example, or a read, depending on where the source and destination is located, the HDF5 library will look at that read or write call and then basically look at its internally registered type conversion functions. And if it finds a matching type conversion function, it will just go ahead and invoke that function and everything will be fine. And that's exactly what we are doing here. So the trick is to define a conversion function, which is like you can think of it like a callback, to define a conversion function that maps from a bit field type to this compound data type in the file. And so here's how we would do this. So, well, first of all, although our compound type is going to live in the file, we have an in-memory representation here of what an element of this compound type would look like in memory. And that's basically what we do is we cast the bit fields that we have into this type, and then that's what we run with. But so this is the in-memory representation of our compound type, which is, as I said, we have a 32-bit bit field, so we just take two unsigned 16-bit integers, and we call the fields low and high. And we call this type the low-high type. And this is the actual conversion function. So if you go to the HDF5 reference manual, you will see there is a function called H5T, so it's everything to do with types, H5T register, and that has a lot of arguments, and we'll see them in a moment. But one of the arguments in H5T register is basically a function that does the conversion, and that has a lot of arguments too, and we'll quickly talk about them. But you basically, any function with this prototype that you implement, you can register as a type conversion function. And then, yeah, the HDF5 library will invoke that function if necessary. And you have, interestingly enough, also the same way that you need matching opens and closes for resource management in HDF5, you also need matching register and unregister function in the sense that, yeah, once after you register this type conversion function, it's just good practice at the end, or once you don't need it anymore, to unregister this function. Now, okay, not surprisingly, so I call this function, yeah, bits or bitfields to compound. And here, the first argument is the source type, so the type from which, elements from which you want to convert into the destination type. So here is the handle, the HIDT for the destination type. Then what looks a little obscure here, this H5T underscore C data T, that is basically, you can think of as a context. So this is where you can pass information about that operation. So for example, this, if you look up the documentation of this, first of all, this struct will tell you something. It has multiple fields, but one of the fields is, for example, the command. So when you do a data type conversion, you can think of it, there are in a way 3 commands. The first would be you want to initialize the data type conversion of one or more elements, and so that gives you a chance to initialize your conversion pipeline should that be necessary. Then the second command is the actual conversion itself, where you have a buffer of elements of the source type that you want to convert into destination type. And then the third command is basically sort of the finalize or the shutdown, where you can do certain operations that maybe require freeing up certain resources that you use internally to make that conversion happen. So that's what in this structure, you can go in the reference manual, check that. Then, of course, yeah, we have to tell this function how many elements we have in this buffer here that we would like to convert. If you remember hyperslabs and things like that, there may also be a stride associated both with the buffer, and then there is a so-called backing or background buffer. So certain conversions, especially if the size of the elements changes between source and destination types, you may need a sort of a background for swapping or for other purposes, background buffer that you can pass here. And then there is just a data set transfer property list that may hold additional information about the read and the write, or which type of data transfer operation you are looking at. And that's it. So it's a mouthful here, but yeah, for data type conversion, you have a lot of flexibility to implement that. And you see here, and then it returns an HLRT, but you see here already, as my first statement effectively in here is to look at the C data structure and to basically understand, well, in what context is the library calling my conversion function? And as I said, the first is I get sort of a chance to initialize my conversion pipeline should that be necessary. And in this case, I'm just printing that, hey, I'm initializing this conversion function, but I'm not really doing anything because in this particular case, there isn't really anything to do as far as initialization is concerned. Jumping ahead here, likewise, if the command is h5t_con3, basically, release all the resources associated with conversion. There's nothing to do here, so I'm just printing a message that says, hey, this conversion pipeline is shutting down. And then the actual workload or the action is really sitting in this when the conversion action or the conversion command is, well, now convert something. And so in this particular case, again, just to make it a little more interesting or show that we can do things, but not too complicated, this is the actual conversion function. Remember, we have a 32-bit bit field. And what we do is low high t, remember, that was our struct where we basically recast our 32-bit chunk of memory. We cast that as two 16-bit unsigned integers. So I'm just casting that pointer here. And then an element, remember the callback, the arguments will tell me how many data set elements we are about to convert. And then, yeah, what I do is I basically use a swap, and I come back in a moment. So it's basically a loop over this buffer here, where we just save the low part, overwrite the low part with the high part, and then restore the low part. So we are basically flipping the low and high part. There is a question, Robert.
Gerd, I'm not seeing your screen as usual. Is that intended, or do I have something wrong on my end?
No, not intended. Yeah, I thought I'm sharing my screen, but let me do this again. Better? Can you see my screen?
Now I get the message that says you've started screen sharing, but it is. There we go. We're good. We're good. Yep, that's it. Thank you.
Okay, good.
Okay,
Sorry.
now we're back to normal.
Yeah, there's something going on with Zoom, and I don't know what. Sorry. So yes, so as I was saying, this is this conversion function. This is sort of the vanilla prototype, and in this particular example, we have nothing to do during initialization. We have nothing to do during finalization. So we are just printing messages, and then during the actual conversion, we basically, we take that 32-bit bit field, we split it down the middle, and then basically flip the low and high bits and cast them to unsigned 16-bit integers, and that's it. And that's what our conversion function does. Part of the reason why I did it this way was also obviously this function is sort of its own inverse. So if I apply this function twice, it just reverts to the original state. So I can use this function to convert from a bit field to a compound of two 16-bit integers for writing, but then I can use that same function also for reading by just flipping the source and destination type arguments, because I know that this function is its own inverse. And but we'll see this in action in a moment. So this is our conversion function. And again, usually in here, people do sophisticated masking operations on these bits, because in this bit field, sometimes only a subset of the bits is meaningful, or different bit combinations represent different quantities. So you can completely knock yourself out here in terms of doing very complicated things. Okay, main. One of the predefined in-memory bit field types would be H5T native B32, and I store this handle in this bit field variable. Here I create my compound type. It's just going to be 4 bytes, and it has 2 fields, low and high, and each of them is an unsigned short. So that's all good. And then this is what I said earlier. We are registering, so you have to register with the HDF5 library these conversion functions, and the first argument here indicates what kind of conversion function it is. So in this case, it's a soft conversion function, as we say, a user provided. Hard would be another one. And then you just give it, this is just for user purposes, a symbolic name. So I'm just calling this a bitfield to compound. And then, yeah, you provide the source and destination type. So we are going here from bitfield to compound. And then, yeah, the function pointer. So this is, I called my conversion function bit to compound, and this is just, yeah, the function pointer. So I register this function for writing. And then since I know that I'm just swapping upper and lower bits, so to speak, I know that this function is its own inverse, so I'm registering it once more, but this time you notice that I'm swapping the source and destination types. So I need this on reading when I'm reading from the compound and I want to go to the bit field. The source and destination types are sort of flipped and I give it a different name, but I can use the same function. Again, the library doesn't care if I use the same function pointer. And in general, again, you will, there's nothing wrong with having one function that implements sort of conversion in different directions or something like that. I mean, it's not that, I shouldn't overstate it. It's not that common, but yeah, nothing prevents you from doing it. Okay, and then just to make this interesting, I'm creating some very predictable sample data. So I create sample data where for each element in the bit field, there's one bit set. So I just take these powers of 2, and I have 32 of them because I have 32 bits. And so for each of my sample elements, one bit is set. So I get this array of powers of 2 if I interpret that as integers. And then, by the way, I'm not showing it here. You can use these user-defined type conversions not only as part of read and write operations. You can also, if you have a buffer in memory that has a data set element representation, and you would like to do a conversion in place, there is this function called H5T convert that will do that for you. So H5T convert, again, you have to specify source type, destination type, how many elements, then the buffer containing the elements, and then there are a few additional arguments. This is an argument for this background buffer, which in this case we don't need. And here's just a data set transfer property, which again is not needed in this particular case. But if you want to experiment with this without writing an actual file or data set, you can do that with just the H5T convert function. Okay, but in this case, just for the fun of it, we want to create a file. And so I call this file compound.h5, and it has 32 elements. And for some reason, I call them shorties. They're unsigned, but they're shorties. And then I just invoke H5D write and H5D read. And what that means is really as a side effect, because as part of calling H5D write, there is a stage in the H5D write operation where the library basically asks, oh, do I have to do a data type conversion? It will certainly ask, do I have any hyperslab selections? Do I have to do any kind of gather-scatter operations and so forth? But as part of that same I/O pipeline, the library will ask at some point, do I have to do data type conversions? And in this case, it will see, oh yes, I have bit fields in memory, but I have a compound type in the file. I need a data type conversion. And then it goes to its internal lookup table and says, do I have a data type conversion available, either a hard type conversion or soft type conversion that can make that work? And the library will say, oh, yes, the user registered these type conversions and they are just a perfect fit. And then it will just go ahead and invoke your type conversion function. And I do the same to show the reverse with the read. And then I just print it out. So what we would expect is that we get the identical output. So we get sort of this list of powers of 2 and the list of powers of 2 here, same list. And then we would expect to see these output messages where it says initializing conversion, doing conversion, finalizing conversion, and then if we run H5 dump on the output file, we should see the compound type with the short or the unsigned short element. And so I did that, and I'm trying to see where did my terminal go. Right. So if I the font might be a little too small. How do I make that? Font. Can I make this font? This is something dumb. So let's just run it. So you can see it just prints these powers of 2, 1, 2, 4, blah, blah, blah. And you see these printout messages, initializing conversion function, converting, initialize. So this first pair of initializing conversion function, converting comes from the H5D write. And then the second initializing conversion function, converting, comes from the H5D read. And then in the end, we see finalizing when we do the unregister, finalizing conversion function. And if I quickly show you the H5 dump output, H5 dump, I call the file compound.h5, you see already, okay, this is, it has my shorties, compound data type, it has low and high fields, there are 32 elements, and then you see, since we swapped low and high on the right, we see not 1, 0, we see 0, 1, 0, 2, 0, 4, blah, blah, blah. And then, of course, since we split it in 2, then we see sort of the inverse for the remaining 16 elements up to 32,768. So we have compound in the type, in the file, we have bit field in memory, and we can sort of, without any problems, go between the two data types. Okay, does that make sense? And then, so data type conversions just do what they say on the tin, so to speak. And sometimes they are just what you need. Again, don't confuse them with filters. However, in the past, we talked about user-defined functions. With user-defined functions, it is actually possible to implement data type conversions in double quotes via filters, but of course, at the added expense of a new data set. So remember, user-defined data functions was basically, you can take a piece of code that can depend on other data sets, like a mini workflow, to create a new data set, to create new data set elements when you invoke the function. So if, as part of that function, you implement the data type conversion, yes, and since the vehicle to implement user-defined functions are filters, in that sense, you could argue and say, I can also use a filter to implement a data type conversion. Yes, in that sense, but only at the expense that you create a new data set that holds that code that does the data type conversion. Whereas with the data type conversion HDF5-style, you just register that conversion function and you just have one data set. You don't need a separate data set because that data type conversion function, that code, is not really represented or materialized as yet another data set. Okay, and we are out of time also. I apologize and for all the technical difficulties, but I hope that was somewhat helpful. And I wouldn't say it's a feature that is used very often, but then again, in cases like experimental science and so forth, it's sometimes just the thing that you need. And it works very seamlessly, and it's been there, from probably, I forgot if HDF5 version 1.0. I mean, HDF5 1.0 for sure had data type conversions in the sense of hard compiler-generated data type conversions. But very early on, I think this user-defined aspect came into the mix very early on. Okay, well, thanks for coming, and enjoy the rest of your week, and hopefully I'll see you next week.
Thanks, Gerd.
Bye. See ya.